Okay, so welcome back. Next we have Paul Lessard, who's going to talk about Spectra, the open finite Z-Groupoids.
Right, hi, Paul. We figured that out. This is just a thing. So at first I should sort of thank them for organizing. Right? This has already been really fun, and I'm really particularly grateful to have an opportunity to speak in an environment wherein some people might actually care about what I've been thinking about. Although that comes along with certain other caveats, which is now I have to know what I'm talking about, which makes it a little bit more threatening. But that's okay. Another thing is I used to have this mantra of, you know the phrase, I am but a simple country lawyer? Familiar with this phrase? I used to really enjoy it, you know, and it sort of gave me something I could say when I was particularly nervous in a context like this, but I realize now that this is a quotation from Sam Ervin, who, despite bringing down Nixon, was also like a rabid segregationist. So you can't really use that particular quotation to feel good and sort of calm. Okay, so now I've said enough so that I at least feel that I have some sort of understanding of the space around me. So I want to give what's probably the most naive of the talks. I mean, definitely the most naive of the talks today, and I assume, you know, the most naive of all the things that will be presented here. I'm going to tell you about Spectra as locally finite Z-Groupoids. To describe exactly what I want to do, I'm going to give you an essentially algebraic theory. Yeah, I was proud of that one. For spectra and a naive stable homotopy hypothesis. With a view towards that. So, oh wait, I should explain why I've written down this one sentence. So, by this first, essentially, that of course mean up to homotopy. By the second one, I mean actually a sketch in a formal sense. Of an essentially algebraic theory. And then by the second thing, I can just sort of begin with the analogy that motivated this question to begin with. So, if in what, the mid-20th century, we've got spaces all the way over here, and type theory all the way over here, a couple of things have happened to connect them into the world that we now inhabit. The first of which, at least maybe it's not right to say it's the first, or at least homotopy hypothesis, that what spaces is equivalent to infinity groupoids. It's then in reference to this that, you know, apocryphally speaking, type theory mutates into that behemoth of homotopy type theory, which we can use to reason about infinity groupoids. But this is only a story thus far. Tale of unstable homotopy. What if we want a similar story, but for stable homotopy? So, in that situation, way over here we have spectra, and then way over here we have linear type theory. There are conjectures that we could homotopify linear type theory and end up with the appropriate type theory for spectra. But what happens in between? That's the question I want to ask. I want to say, before I talk about what I've done and what I want to talk about today, I should mention that when we restrict to connective spectra, there is a stable homotopy hypothesis of Gursky, Johnson, and Cerno, which puts connective spectra equivalent to Picard infinity groupoids. And I know that with adequate and appropriate stratification, we can actually prove this in the case of stable 1 types and stable 2 types. And it's very well possible that this is the kind of perspective that we should be looking at if we're going to try and come up with some sort of stately homotopic linear type theory. But it's not what I want to talk about. Instead, I'm going to introduce you to what I'm going to refer to as the naive stable homotopy hypothesis. If I had any more fearful adjectives to apply to stable homotopy hypothesis, I would put them in there. But, so what's the story I want to tell? Okay, yeah, follow this. So, the story that I'm going to tell you begins, and this will all become more clear and more explicit, with the fact that models written in delta with respect to the spine inclusions give you 1 categories. Models written in theta 2 with respect to the spine inclusions give you 2 categories. This can, of course, be completed going up to models of theta with respect to the spine inclusions. Give you strict omega categories. And then we can extend that in a natural way to define Z categories.
So these spine inclusions you mean as the distinguished cones of the sketch?
Yes, exactly.
Will you explain what these are?
Yes. No, I have some good advice about writing this talk, was make sure that they have the story of what you're doing at the beginning in case I don't finish. I think that was probably pretty solid advice. But yeah, no, I will explain all of this. In particular, I will go through very carefully how we start with delta, then get theta 2, et cetera, all the way up to theta, and then go the opposite way. Right, so that list can be extended to define models of what we refer to as the stabilization of theta, again, with respect to the spine inclusions. Can be used to define Z categories. And then we'll get to what I'll actually tell you, but by the time we get there in more formal means, you'll already believe it. That's the following theorem. The full subcategory of point appreciates on what we'll refer to as the stabilization of theta, and this subcategory we'll refer to as J spectrum. Subtended by those objects which are locally finite, in a sense that will define the point is these are natively, the cells of such a thing are natively going to have infinitely many faces, and we're going to put the hypothesis that in fact they only have finitely many non-trivial ones. So that's what this local finiteness is going to be. So subtended by those objects which are locally finite, admits a model structure which is first intuitively understood as presenting weak Z-Groupoids, and perhaps more importantly, equivalent to the HoTT model structure on spectrum objects for how you can point at cellular sets with respect to suspension function sigma j, which is where all the matching is going to happen. So exactly in this choice of sigma j. So QE to this stable model structure. So, of course, I haven't said exactly what many of these things mean. So let's go ahead and get there. I want to begin with one of my favorite stories, which in the spirit of Kipling might be referred to as how the quasi-categorical that its compositions, or more reasonably, why quasi-categories present infinity one complex. So we begin with the observation that object-wise, delta is generated under the operation, delta note like this, garbage there and garbage there, which will be the expected push out over the initial, final, or excuse me, final and initial monomorphisms from 0 into whatever. And we'll refer to this thing as 0 going to a sum. So I said object-wise, meaning I'm just saying that the objects you get all of those. You don't necessarily get all of them. So you actually get a little bit more delta in order to get all of those. The subcategory, the truncation of the reflexive lobe category, comprised of one object or two objects. And all those maps we expect. So we can then define exactly what I meant by these spines. So let En inside the delta and be the sieve generated by the family. That's too low. This is, of course, the map 0 to 1. This is n minus 1. And you went through all the other ones. The point is, En is still naturally associated to the zero glossary representation. And in particular, the observation. The co-limit over to the end. Is isomorphic. We can make formal exactly what I meant by a model. So a model or the sketch dealt together with these distinguishing sieves. Is a pretty sheaf, which preserves those limits. And the thing that I sort of just began this whole story with was that models, with respect to this particular description of specific cones, or whatever I say, gives you back one categories. Right, in particular, the reason is that you recover the fact that every n simplex of your simplicial set is specifically given to you as some composition of other things, right? That's the point. You're encoding this operation by way of the isomorphism between the globular presentation of the thing and the thing itself. So, before I say what I'm going to say next, I want to find something that probably has like 10 words in it that we're just going to treat as a black box. So, good appreciate topos, appreciate on A. This is Zinsky. Model structure on A. Specified by the localizer. I'm going to underline a bunch of these words so they're all just one thing that we never have to investigate too carefully. So when I'm saying give appreciate topos on A. Zinsky model structure on A specified by the localizer. Okay, what the hell am I? So you have S. Is the model structure on A. Excuse me, appreciate on A that satisfies two things. As the smallest class of weak equivalence as possible, and two, both iterations are monomorphisms. Right, so the whole point of this story is then it's sort of obvious, or so these reason I'm going to grab more of these and just start reading. This one's better anyway.
Sorry, where do the horn include, or the spines come in the specification of the model structure?
So that's, I haven't said that yet, right? So I'm just giving you this black box of Zinsky model structure on a pre-chief of most specified by a localizer. I just don't want to get in too deep. The point is that, as I'll just kind of point, is that you got to believe almost immediately that Zinsky model structure on sets specified by the localizer above spine inclusions presents infinity one categories. that aspect is suddenly obvious if you've gone through this particular story. Right? The point is, of course, it's just the things that are weakly left exact with respect to what limits actually exist. So that's makes a very nice notion of homotopy sketch. Right? But that's got the big thing, and then the big thing is, of course, that you can actually test how I want it. This is the point, and maybe the reveal is its actual visual L structure. So this is actually visual L structure. And then the big combinatorial miracle is that you can actually test for vibrancy of objects by way of only looking against their horns, as opposed to the significantly larger class of anodine co-vibrations that you would have to consider naively. You would expect to have to check a hell of a lot more conditions than you actually have to. That's the combinatorial miracle, at least. But why it presents infinity one categories should actually be understood sort of quite clearly. It's because it's exactly this notion of being a weak model for this essentially algebraic theory presented by way of this particular sketch. So, why have I told you this story? Aside from the fact that I at least really like it, so I'm going to subject almost anything to it. But the reason I've told you this story is it begs the question, what can we do for week 2 categories and week 3 categories, etc. So this section I will note as how then the 2 categories. So here we begin with Berger's reconstruction. A category with delta reached with A. Category objects. The objects are objects of the simplex category together with n objects drawn from the objects of A. So n is an m, and the tuple AI is in the objects of A. So it's category on those objects. I'm not even down to this. Humanizing is not the word, but something can really be able to. Between n and A1 again, and m E1 through Bm, a set of simplicial morphisms phi m together with a tuple of multimorphisms, which I'll refer to as boldface F upper I, such that phi, well, I guess I've already said what it is, overdetermination or something like that. And then each one of these Fi is a multimorphism from a lower I. First into B, phi I minus 1 plus 1, and B phi I. Now, it's always bothered me that that description right there is as complicated as it is because it's such an elegant notion. And so I'll just present to you an example of what such a thing is. I've labeled this arrow by A1 and this arrow by A2, B1, B2, B3. Now there's the map dots is the underlying simplicial morphism. That's F upper 1, and the pair of these things is F upper 2. That's the game. one should morally think about what this wreath construction does is gives every one arrow a cross section of shape, whatever object you label it. So, as I get to leave that word up there.
So what's the shape in that example there? Of the one arrow?
Oh, sorry, the shape here is this object A1. So I imagine that this is, so I'm sort of indexing I'll just give you a more clear example in the context of delta root through delta, i.e. theta 2. So this is 1 with 1 root delta. Right, and then the morphisms that you expect to get, which are straight 2 categories in this case, are exactly like that. Right, so I can imagine doing this, this, and this, and then if I had the morphism which stretches this thing out over the whiskering of this 2 cell with this 1 cell, I get this thing goes to that composition, this thing goes to this composition, and then how do I do that? By this going to get, this is the identity here, and then the degeneracy right there. Right, so this is one way that you can inductively construct these strict N categories. Yeah, so that's what I mean by cross section. It ends up being quite useful because we'll eventually come up with T cross section spheres in any dimension.
So are these now examples of morphisms in the wreath program?
Yes.
Could you say what other?
Okay, so what I should say is like this. So this is an example of one, and then the morphism here is the identity, and here is S0.
Yeah, so you can, this is a full subcategory. If you look at C and you look at pre-sheaves on C, this will be, as long as C has a terminal object, this will be a full subcategory of categories enriched from pre-sheaves on C.
We'll have more examples. Actually, right. So definition. Theta 2. You delta root for delta. So just as in the case of delta, we had this really nice lemma that said that all of the objects thereof, at least, were generated under this notion of zero globular sum by the truncated reflexive globe category that goes up to 1. We've got the exact same result, but with more kinds of Ur composition. Right? We have only one abstract notion of composition given to us by zero globular sum, but in the context of 2 categories and eventually in higher categories, we need more and more notions of composition. So we get an analogous structure, or the analogous claim. The objects of theta 2 are generated by truncation of the reflexive globe category at 2, which is just 2. How am I writing 2 here? 1 raised with 1. 1 raised with 0. And 0. So under the operations, zero globular sum, which is exactly as it was before, and 1 globular sum. For this is not defining everything. But the point is, it's consecutive 2 sets. Given that generation hypothesis, so infinity of t, non-tangent theta 2. Presentation t equals n1 and 1 over to n l minus 1. And we may let the spine inclusion be the exact same kind of thing it was in the case of simplicial sets. The point is, it's exactly the sieve that is generated by this globular presentation. But the point is, I can be doing 1 cells, 2 cells, and 0 cells in all of these different ways. But nonetheless, the notion of the spine is preserved. So,
is this a sort of like pasting chain, or is this a whole pasting diagram? And then
it is a whole pasting diagram, but you do have some hypotheses of what kinds of things you can actually get. Right, I can't possibly have holes. I believe you can say that these are like simply connected intervallic, pasting diagrams in strict whatever categories. I believe that's the sort of the formal nonsense that one could say that says yes to your question. And so let this be sieve associated to the globular presentation. So that means it's the sieve generated by the family of maps and one entity all the way up to that entity. Right, now use this over bar to indicate that we're adding dimension by going into higher lobes as opposed to composing things to get more dimension out
What theta 2 here for this theta?
Yeah, I mean I've only defined 0 and 1 globular sum at the moment, but yes. Yeah, so admittedly, I've only said that we've got 0 and 1 globular sum, but the point is that description that I've just written up there is actually going to hold for all of theta instead of merely this truncation to only allowing composition to 2 cells. And then the reason we've done all this work is that it is indeed the case that models for theta 2 with respect to these particular spine inclusions give you a precipitation of strict 2 categories. Right, and then there was for, I don't know how many years, Eric, you probably know how many years this conjecture was
I
open.
think it was open in 2006, and I was the first one to find a counterexample in 2010.
Okay, and it's the same counterexample that Aral mentions, right?
His is more developed, but I found out one specific counterexample.
Okay, cool. I just wanted to be accurate on the history of the issue.
Yeah.
Right, whenever you're giving talks and you're nervous about something, you're like, okay, provided these people are not in the audience, you're not going to be too worried. And then you who are not registered, just show up. I confess, I lost a good hour and a half of sleep based on that one fact. It's okay. All right, what the hell is that? I don't remember. Right, so there was this conjecture. Right, the conjecture that was actually stated is significantly more general, but I want to get to that. Right, and that was that a Brzezinski model category structure on theta 2, on presheaves on theta 2, specified by the localizer above these spine inclusions presents infinity 2 categories. However, counterexamples were found. And in particular, the counterexample that we're just going to write down suggests something spectral in an interesting way. counterexample is, so let I be the minimal groupoid on 2 points that has all simply connected and all that. Usually, I've had this joke just like running in my mind for years since I first heard people use the phrase free swimming or free living interval. And I just always want to say, like, no, we should call it the libertine interval. I sort of really enjoyed that. It's a moment. Okay, so let I be that thing. Let 1 produce with I. We can co-limit over the cells of I. Of 1 beat with those cells. Well, the projection from I down to the point is an equivalence of strict 2 categories. Is an equivalence of strict 2 categories. And so too, one wreath with I down to 1 wreath with 0. It is not the case that 1 wreath with I down to 1 wreath with 0 is W equivalence. In the model structure we've mentioned thus far. Now, this is sort of where I want to stop the story with regards to infinity 2, infinity 3, et cetera categories. The thing that I want to observe is just in this presentation of theta, this 2-point suspension is doing something interesting. And there's more to it than we might immediately assume. Right? Just putting this simply connected groupoid on 2 objects above 1 somehow breaks things in an interesting way. So there might be something to do with this 2-point suspension. Right? And so that's where I want to go back for 1 step. So we not go back 1 step, just observe something.
Why is this suspension?
So if you imagine those things as paths, and so if everything is just made groupoid, what this is this is exactly the suspension that one is familiar with from the book, right, for the 2-point suspension, because what we've done is, so we took some quality like this. What have we done? We've then replaced that with an equality between 2 equalities of this point. Right, so in terms of the category business, that's exactly what we've done.
Yeah, also the geometric realization is isomorphic to the 2-point suspension. There's a geometric realization functor for these things, and it's saying that you're suspending something that's contractible and it's no longer contractible is a problem.
Yeah. So what I want to say then is, all right, two obvious functors. Delta into delta wreath with delta. Right. The first, you sort of used implicitly already more than once. We assign n to n and a bunch of zeros. But there's another one. So let's call that one U. There's another one, let's call it J. Sends in. To one wreath with the object in. So, as it so happens, if we keep extending delta along this, we'll get the theta ends and eventually theta. But we can also extend theta along this. And the trick with doing this is we'll end up naturally with a notion which is a sketch for the theory of Z-categories. All right, so definition. Theta n. The n-fold wreath product of delta with itself. Let theta be co-limit in the category of categories of delta by u into delta wreath with delta by delta wreath with u into delta wreath. There are only 3 I should draw it. And then you get the point. And theta lower st for stabilizing theta is a co-limit over the induced functor j. Theta by j into theta by j into theta. And then the thing that we should observe is just as for delta and for theta 2, we had this lemma about delta being generated under zero globular sums by the truncated reflexive globe category, truncated at 1, and theta 2 was generated by the reflexive truncated. Reflexive globular category truncated at 2. Theta, the untruncated, theta is generated by the untruncated one. It'll turn out that this is generated under the analogous constructions by just not truncating the reflexive globular category at 0. Object-wise, theta is generated by GR. The operations of globular sum where I is greater than equal 0. Stabilization of theta generated by what we can refer to as GZ. By the obvious notion of Z globular sum over all of Z. And the reason we've done this is because we exactly get this notion of horns once again, or excuse me, not horns, we get this fine conclusion notion just again. Right, so this is why it makes sense. There's a reason one writes notes. I always forget that reason. Okay, that's right. Oh, right. So
So I guess there's 5 minutes left.
what?
I guess you have 5 minutes left.
Oh, shit.
So did we start on time now? I should ask.
We didn't start on time.
Okay, so maybe you have 10 minutes.
Okay. So then I will try and blast through this because I don't really want to belabor everyone forever. Right. The corollary to this is that the models for theta and the associated spline inclusions here, this gives you strict omega categories, and then you can extend that by defining strict Z categories to be models for the stabilization of theta with respect to the analogous spline inclusions, which again come from the globular frequentations. Okay. So I've said the word suspension, and now I guess there are 10 minutes left, so I should probably find Spectra as soon as possible. Seems like a reasonable premise. So here's what we'll do.
Z Z-graded categories.
Exactly. There are no objects anymore. It's just turtles all the way down. Right. In some sense, this is sort of the point, right? My totally naive dream with this entire concept is that we could come up with some way to talk about spectra type theoretically without ever presuming that the topological or even the homotopical structure of the thing is endowed iteratively by forming identity types. Everything's always an equality between two different things from the beginning, right? And that you have, and it just goes all the way down. Like that's sort of the moral goal behind this whole thing. Is that I was hoping that maybe we could figure out some way to talk about spectra just as this eternally relative quantification, sort of analogous to how in cubical type theory quantification over specific shapes has turned out to be so helpful. Imagine if we could do quantification over spheres and make that a particularly natural notion. Right, so the thing that I want to say is, so
is it like naively a thing that where the objects themselves have some internal structure or something?
The objects themselves are morphisms between some lower morphisms all the way down.
So you have n cells for each integer n, and the domain and codomain of an n cell are n minus 1 cell, right?
Yeah. All right. So then what I should say to try and get this done as quickly as possible is, so sigma j from theta into pointed precies on theta be the functor which associates with cell T. Precies theta 1 reached with T. Now the important thing to note is this functor J was not full embedding, right? It was faithful, but it wasn't full. In particular, you had the emergence of these two new zero cells, right? To form the reduced suspension associated to that 2-point suspension, we should glue those things together, right? And that's exactly what we do. So modulo the boundary of theta upper 1. Right? It turns out the conextension of this thing to pointed cellular sets is left Quillen. Incorrect in the sense that it has the correct universal property, but in particular, you can actually show that purely combinatorially without any reference to geometric realization. And in particular, that's a really fun thing that has to do with as you take the 2-point suspension of morphisms, you're reorganizing what kind of composition is happening, right? And so if you want a degeneracy, you have to reorganize that composition, right? In particular, so this is just something that I get excited about, and now I'm doing that thing where I get off the notes and things get wonky, but sorry, I have to, it's too much fun. So the point is, if I take the 2-point suspension of that thing, I'll get this. I want there to be some obvious degeneracy from here on to here. Right? In order to construct this, what do we have to do? Well, I don't want to mix things. I still want it to sort of read the degeneracy here off, followed by the degeneracy here. So what you can do is that and this cell goes to this thing, this cell goes to this thing, and these obviously go there. Right, so that's the point. So you can coherently reorganize the order of composition, right? And that's exactly what the special degeneracy that allows you to show by purely combinatorial means that this functor enjoys the right universal property.
Sorry, what is the proposition? I can't read it.
Sorry, I didn't finish it because I got spazzed out. So the point is the left con extension to pointed cellular sets is left Quillen and correct, meaning that it does, call it of sigma j, right? So I've claimed implicitly that it's some sort of reduced suspension. The point is, it is. Yeah, I mean, it's sort of, you believe that it's obvious at this point. But the thing is, here's where the nice thing happens. The obvious way to stabilize pointed cellular sets of this suspension is, of course, to take spectrum objects valued in pointed cellular sets and then look at the stable model category structure on them as described by, say, Hovey. But there's this other arcane construction due to Kahn that observes if I happen to have a suspension functor like this that actually factors first as an endomorphism of theta and then something else, I can first stabilize theta and then just look at those pointed presheaves which satisfy the appropriate vanishing hypotheses. And that's exactly what we can do. So what factorization is implicit here is it's that one J, right? It's doing the 2-point suspension on the category theta. Okay, so then the point is definition of J spectra inside pointed presheaves on the stabilization of theta. The full subcategory of that target such that for all TZ, what the hell do I mean by this? Right, that's a reasonable question. So the point is it's a T-shaped cell which has been planted at level Z. Right, so the point is I've taken a T-shaped cell and then freely adjoined sources and targets all the way down. Right, so for all of these things, for all X, okay, implicitly this capital X was of course one of these things that I'm subtending the subcategory provide. Right, so for all X in X of TZ, there exists some N such that any chain of monomorphisms of the identity and these are in the stabilization of theta, or Fn F1. And so the point is, the combinatorics of theta are significantly more complicated than those combinatorics of delta. In particular, writing down what arbitrary, chains of n monomorphisms is actually a pain in the ass. Right, so we can simply avoid it. But the point is, what is this? This is just taking the face operation of face operation of face operation of face operation some finitely many times. The point is, provided you look only at those presheaves on the stabilization, on the pointed presheaves on the stabilization, say that such that there exists some n for which any chain of monomorphisms in theta stabilization, such a thing, you have that. Do implicitly, things are going to go backwards, but I'm not going to write that down. The point is, if you apply that associated chain of maps, and I haven't done the countervariance, sorry. Okay. All right. So the point is, if you look at these things I call J spectra as a subcategory of pointed presheaves on the stabilization theta, right? So these are morally Z categories with no composition law necessarily whatsoever, right? And these are those Z categories wherein every morphism is actually a loop, right? So that's every cell is actually a loop at some level, just with some cross section. That's exactly what these things are. And I'll just get back to the point. Which is that theorem that I wrote down at the beginning. Stop. The point to the analog to the Jasinski model category structure on Facebook as a subcategory of pointed presheaves on the stabilization. Specified by for cells of theta, there's an analog to the generic horn, right? But instead of being indexed by a specific number, it's indexed by some specific degree 1 coface, right? And so let's just call that lambda kappa into theta t. right? And the point is, so this is filling for a hole. Sorry, I forgot one thing. What do I mean by FZ of that? I mean the expected suspension spectrum at level Z of this notion. Right, so then it makes sense to believe that these things are, what am I saying? We locally finite, we Z-Groupoids. That's the thing that I'm saying, right? So this model category structure specified by this is equivalent to spectrum objects with respect to this Joyal-induced suspension functor sigma j that I spent so much time describing. And I think I can stop there. Right. The point is, this means that this purely combinatorial gadget gives you an intuitive description of spectra, and we know through exactly this process that it actually presents the correct category. Right. I apologize for having gotten very spazzed out and started missing words and letters. Right. Those are things that are missing there. I accept that. Apologies, but the point is that through all of this sort of stuff that is just lying around, there is this incredibly clean, simple description of spectra that says, okay, I can maybe think about spectra as locally finite weak Z-Groupoids. And that gives you this really naive stable homotopy hypothesis, which is significantly, or more naive, I'll just say that. Yeah. Whatever. Okay, I'm done. Thanks.
Questions?
Yes, sir.
What do you know about the weak Z categories without this, not caring about spectra?
That is why I did it this way, but I don't know yet. The only thing is that I know that when you do weak Z-Groupoids, you get spectra. Right? Implicitly, this thing is all set up to see if I go for weak Z categories.
Do you still have to localize at the suspensions of the interval?
To get the group, to get this notion of groupoids, no, you don't. It just follows from sort of Kahn and Hovey magic. And actually, a very nice formal reformalization of Kahn's original construction that sort of beat me to the punch on talking about that stuff was put out by Chen Prison Poulter a couple of years ago. And that has a really nice description of Kahn's construction. You can sort of see why you actually don't need to do anything else just to get spectrum.
Yeah, but for the Z categories.
Yeah, for Z categories, I would assume you would have to, but I don't know. Actually, that's the thing. I don't know if you would have to, and my hope is that you wouldn't. And the reason you wouldn't is because that problem was inherently an unstable problem. And when you stabilize that problem, it goes away. That was essentially, well, that's one hope. But the honest answer is I don't know, but I hope.
Oh, one other question. Do you have a good description of these lambda kappas now? In the old days, these were really annoying to deal with. Like, can you relate them to spines and stuff now?
No, they're still really annoying. Yeah, you just know that they work. They're not terribly nice to write down, but the point is, you should be able to. Something that's nice that you can do. What I think is a good idea to say is that you can definitely just describe a spectrum as being presented entirely by globes, and then just say, well, no, I'll just algebraically complete these under the operation implicit area. And so that's probably the closest to a nice description of things that I've come by thus far. And that's sort of the hope with regards to connecting it to type theories that you can actually use. Talk about it Z-globularly, and then just know that there's some algebraic structure. Yes, sir.
So the full Z category is weak all the way up, all the way down, not necessarily invertible.
Yes. Good. Although, to be clear, I haven't defined that notion. Right, it's just sort of implicit in what's going on. I know what strict Z categories should be, but in terms of exactly what weaknesses should be involved for that one, I can't say. But I know that this is definitely the notion of groupoid associated there too.
So I'm wondering if we had so I don't know, do people know the HoTT hypothesis for theta groupoids?
Yeah.
Is this true?
Yeah, Szynski proved that theta is a test test model structure.
Okay, so you get it.
Yeah, it's something like 2011 or something.
Yeah,
So I was wondering if
Yeah, all the theta ends are, and then there's this beautiful construction of how wreath products and decollage work, where decollage is this sort of very nice sort of lepton extension way to construct cones. And they figured out a way to wreath cone constructions over delta.
I'm just wondering if, I was wondering if it was a formal consequence of something like that you got, or like Spectra here. I mean, is that what you're claiming?
That's pretty much the point.
Okay.
Is because those are spaces,
Okay.
if you find, like, and frankly, you should be able to do all of this with any data. I just happen to choose this particularly nice thing so that there's a very sort of categorical interpretation of the suspension.
Yeah, because you say here that it's equivalent to this other stabilization, but I just wasn't sure if that was a known homotopic model for.
Yes, it is.
Okay. I see.
Yes, sir.
Maybe it's only a question, but maybe an open invitation for people to say something about this idea that the spectra should be like some categories where the objects themselves have some structure can go all the way down, turtles all the way down. Yeah, I don't know. Do you have any idea, or does anybody have any idea what that means? Or
I mean, it's sort of like compose objects, kind of. It's really weird. Like sort of like compose objects.
right.
And it's like
A good instance to think of this is the stable homotopy hypothesis of Gursky, Johnson, and Morrison, where they've got Picard infinity groupoids. So those are infinity groupoids wherein the objects are themselves invertible. So there's just some, so it's a symmetric monomodal infinity groupoid wherein you have this extra fact that everything is itself invertible. Right, and so if you imagine that algebraic operation, which is just encoded by the, okay, I've just got some product, if that came from composition, that's essentially what I'm saying here. Yeah, so one of the next thing to do is actually to connect this work with theirs and see if there's compatibility or not. Yes, sir.
I don't know, you may be aware of this, there's an interesting proposed example of a non-invertible Z category. And I think I learned this from Peter Lumsden. You remember this too? Like, so you take, like, it's actually an omega opt category, so it's like trivial above in positive dimensions. But so the zero cells of the objects are sets, and you say, well, actually, a set is the same as a functor from the terminal category to the category of sets. So your zero objects are morphisms, are functors, which means that your -1 objects are categories. And then you say, oh, well, a category is actually the same as a two functor from the terminal two category of cat. And so your -2 objects are two categories. And your turtles going down actually go up in categorical dimension.
That's cool. That's cool. It's very obvious.
It's categories all the way down, actually.
Right.
Category is turtles. Send it.
On that note, I thought about invertible only up beyond the fixed point or something. Is this something that someone could be maybe?
I have no idea. I was just looking for spectrum, and then the fact that it ends up naturally described in this much broader category of things is interesting, but I cannot speak to whatever the hell it means.
Okay, should we think those people over on?
I also want to thank Mike Schulman once because I asked him a question years ago.
there's a question on that overflow about this like 2 weeks ago. Should answer.
Well, he was.
Oh, really?
About weak Z categories. Mike left a comment. I don't remember the letter, but yeah, it was out there.
Okay. I did have an podcast 2 months later said that was good.
Yes, excellent.
Can I stop recording? Oh, yeah.